Okay. In who now? No, I'll probably just roll downstairs. Get on number 2.
I have two teachers. I have one big bush here, one big bush here.
I can't.
You have one big bush, I have two. But then one has
Maybe they can hear through my microphone.
Oh.
Oh.
You need network.
Or you can just essentially look over.
Sorry?
Usually on the whiteboard is what you like write equations and stuff. So if you do together, you can probably just
Works
look over at it. Yeah.
It's a day full of bugs today. I don't see.
Oh, I double that.
What do you mean? Oh, the buttons just go out. Yeah. It's right here. Okay, now I can hear you. I can hear people. I don't know if people. Okay, now they can hear me. Sorry for the delay. But we had some serious network problems over here. Okay. So, first of all, you can go to the website, the Meetup website, and download the data set. Has everybody done that? Like if you go to the Meetup invitation, it's the updated where you found the WebEx link. You need to download a Python file and the dataset file. Okay. So as you are doing that, today we're going to present. Is everybody with me? Have you connected to WebEx so you can hear me? Okay. So turn off the voice for the on-site students. First of all, we want to help thank Brian today. He brought us some very nice cinnamon sticks from Alon. Just for the remote students to see what you're missing, okay? Quite delicious. So today we're going to talk about collaborative filtering and how we can build a recommendation system, a very simple one. This is, let's say, about 10 years old technology in recommendation system, maybe less. I think academically the papers were published 10 years ago, but they've been in production for several years, and you can achieve a lot by just doing that. I remember, so when the Netflix competition was announced, I think 2006-07, something like that, this solution was bringing you very, very close to the goal. I think approximately 10% close to what they were trying to achieve, and then the rest 2 years they spent millions to get to the desired result. So, has everybody downloaded the files? Have you downloaded the files? You should connect to the wires. Yeah. Please. So we're only going to need, so Group Lens or Movie Lens is a very popular website that has movie recommendations. And the format is pretty much straightforward. So when you unzip it, you're going to see, in the directory, you're going to see a file called ubase, and then I think there's another one called useTest. So this one has 80,000 ratings, and the other one has 20,000 ratings.
Just to be clear, the data set, or will you use 100,000?
So we can use any of those. But let's start with the basic principles of collaborative filtering or of recommendation systems. You start with, and some of you that are pretty frequent in these courses, you remember what I'm just going to say. So we always start with a very big sparse matrix that, we having users here and ratings. Today, the problem is small. It has only 943 users, and I think we have 1,600 around there, ratings. Sorry, it's users and movies. And here, every user hasn't really scored all the movies, because if he had scored all the movies, then whatever the recommendation system, he has scored some of them, and these are the non-zero elements or the ratings. Okay. And today we're going to have a matrix which is pretty small. It has 100,000 ratings or 80,000, something like that. Now the goal over here is like the very, very first thing that you do in a recommendation system is refactoring this matrix. Okay, so don't worry, all these things, they're going to be online. If you want to download them, you don't have to, unless it helps you. So, but it's going to be there. So just to be clear, we're going to finish since we're late at around 1:30, 1:40. I know some of you have other things to do, and I apologize for the delay. Network problems happen. So what is the idea behind that? Like, we are trying, so every user is a big sparse vector, and we want to assign a low-dimensional vector for every user and for every movie. So what if, think about that, what if there were 10 types of users, 10 different types, the user that likes, the user that likes, police movies, the user that likes romantic movies, or maybe a mix of them. And you could say that Nick seems to resemble 80% to that exemplar user, 10% on the other one, and 10% on some different one. So that's the matrix factorization is really something that you all recognize as clustering. Okay, you might have seen that as a latent semantic analysis, which basically says that each user is not one user. It has some latent factors, some things we don't know. So it's like exactly when you meet a person and he starts talking to you, this is the impression, and you stand now. You have a psychologist here. You say, okay, he seems to be a little of type A personality, a narcissist, romantic. So basically, you assign some latent factors, things that they are hidden inside him. That's what we will try to reveal with the matrix factorization. So basically, imagine as one line of, let's call this the U matrix and this the V matrix. So this line will represent a type of a user. So if we take the extreme over here where we had two groups of people, one group of people that they watched, Die Hard, the Terminator, blah, blah, and the other, yeah, we can see it's like the other table over here, the boys, like the Georgia Tech table over there. Actually, it just happened. You clustered very naturally. It's all Georgia Tech students from there. And then we have the romantic table, whatever, people that they watch the, I shouldn't say that, you're not romantic. You know, people that watch like I Love Actually, and unfortunately I don't know more than that. And and we were doing a matrix factorization, Walk in the Clouds. Okay, Angelo is also romantic. Walk in the Cloud, and The Eternal Sunshine of a Spotless Mind. And, you know, let's open a new whiteboard.
Is activating.
Somebody is activating
microphone. I'm hearing myself.
Microphone, and I'm hearing myself. The echo.
I think it's not Amber.
I think it's not Amber. Yeah, it's you. So imagine now that we had users here. Like, I give you an extreme example, and here we have horror movies, and here romantic. Okay, and here we have men. I'm going to be a little bit inappropriate, call it. I've been on that. Professors nearly lost their jobs because of that. And we could see, okay, I'll turn it around, men rating these movies here, and women rating these movies. So you could very easily turn that into a product of two matrices. Okay. And then so basically I'm trying to highlight the non-zero points. Okay. So basically, if you take the product, let's say the first man over here, and you multiply it with this matrix, it will never really pick. So here's like the horror movies. I think I did it the other way around. Let me fix that. We will see that there will always be a non-zero value over here multiplied with a non-zero value over there. So if we wanted to make predictions about what they're supposed to rate, we will always jump and say they will conclude into rating only romantic movies, while the girls will rate only horror movies. Okay, so that's kind of like a very distinct case. It's like an edge case. And making a small digression here, whenever you think about a machine learning method, before you test it on real waters, on deep waters, that's why we're in shallow waters today, you should test it on the extreme case. What if it was something that I could visually tell without the help of the algorithm? Okay? Well, something that was super obvious. Would my algorithm catch it? So do we get the idea of the factorization? Now, this is pretty well categorized where we have horror and romantic, but it might be the case that there are, and that's where our life is much more complicated than that, where we have some horror movies that they might be associated with some romantic and the opposite. Okay, so things are not really that distinct in real life. That's why we need automatic systems and more complex systems to capture all these hidden correlations. So is everybody with me? Somebody is coughing. Fortunately, he's not in this room. We're not getting flu, but we might get it through the computer. I don't know who it is. You hear myself back to them. Somebody has activated the microphone. And so please keep it mute unless you want to ask a question. Okay? So somebody is speaking silently. I think it's you.
Yeah. Try and turn it off.
Makes me act like the mentalist, for those that work. So we got the idea. The V matrix will have, prototypes, exemplar users, and the U matrix will have each column will be membership to this particular exemplar. Okay, so for a specific user, we will go over here and say, okay, so let's take the vector of user number 21, where it will be 0.1 here, 0.3, blah, blah, blah. it means that it's 10% like this user, 30% like the other category. But now, the whole problem is interchangeable. Like, why do we put user and movies? We could have put movies and users. So we could think the opposite, that every movie has appeal to a specific character. Okay? So now, each line on you can be a specific type of people. You know? So now we can go to a movie. So if you take a slice of the movie over here, this will tell you that this movie has appeals 30% to type A, 10% to type B. And so in the extreme case, if we had, kids and adults, and we were running a collaborative filtering thing, we will see that some movies will have 0 in a specific category, like the kids movies, because they're only by kids. They're only watched by kids, and then there's another one that it's preferred by adults. Now, what is really the beauty of the collaborative filtering? Now, each movie has, or each user, I'm still listening to myself. It's not you. So maybe I should block the audio. Oh, no, I shouldn't block the audio because somebody might call me. So now each movie is a k-dimensional vector, which means that if I want to find out similar movies, all I have to do is to take the Euclidean distance between, this movie and all other movies and find which ones are closer. So if I find the movie that is, has the same behavior on the same type of people, it means that they are similar. Now, the simplest way to do matrix factorization and the most popular and maybe the most powerful and the one we're going to use today. And when we go to the collaborative filter, we're going to see some more sophisticated ones. It's called singular value decomposition. You know that you increase your salary by 10%, maybe 20%. I can guarantee you that if you understand SVD, you understand a lot of things in machine learning, and by doing several tricks with SVD, you can make very sophisticated systems. So SVD will break that into a U sigma P transpose. For those of you that they are mathematically very experts, U and V. So yeah, maybe we should ask the students what are the properties of the U and V matrices. What do you mean by independent? Orthogonal. Okay, and the same holds for V. And there's another thing that actually orthonormal, which means that the dot product is either 0 or 1. Okay, and that kind of like you said that very nicely forms a way of independence. But that kind of independence is not always the independence you want. Exactly the same thing with the independence you get in a relationship and outside of a relationship. We shouldn't really, or married, talk about that. So anyway, now the sigma matrix is diagonal. Okay, we call these the singular values, and they're always positive. So that's a very good way to debug. So the reason why we're mentioning these properties is because we want to address a very big problem in machine learning. You make a machine learning system, and it has a bug. It gives you garbage. Okay. Now you have to be careful why you're getting garbage. And you want to run some unit tests. So one of the unit tests you want to run is that are my U and V orthonormal? So if I take their inner products, are they giving me zeros and ones? If not, there must be a mistake. Especially if one day you want to go and implement your own SVD, because the algorithm is, the constant decomposition is one, but there are several algorithms that they have different advantages for computing SVD. The other thing is that you compute the singular values, you see that they're negative. There's something wrong. They always have to be positive. And if you do full SVD, which means that, if this is 1,000 by 100, sorry, it means that U is going to be 1,000 by 100. That's the full SVD. This will be 100 by 100, and this will be 100 by 100 too. So whichever is the, there's a convention when I talk about SVD, the rows are always more than columns. Otherwise, you have to put the maximum first. Now, so it's a very critical thing. If you get 1 million users and 500,000 movies, you will never going to do full SVD because these matrices are going to be huge. The concept of doing SVD is you're also compressing the matrix. You are extracting information, okay? So never make this mistake to do full-blown. Usually you'll do, your K will be from, 10 to 1,000 or maybe 10,000. These are typical values depending on your data, which means that you're computing the first K eigenvalues and the rest are becoming 0. You zero them out. Sorry. Also, another property of SVD is that the eigenvalues always come in the descending order. You get the first, second, the positive. And if you do full-time SVD, full-scale SVD, and you multiply U, sigma, and V, you will get the exact same matrix. Okay? Now, another property of SVD is that if you do an SVD of order K, and you're getting an error, so basically you can do of order K, and then reconstruct the matrix. The reconstructed matrix will not be exactly the same. You will have an error. Now, if you do with K plus 1, your error should always decrease. Like the more eigenvectors you add, the smaller the error should be. Again, why is this important to know all these things? Just in case, you code your own system and you want to debug it because something is going wrong. This is very important. Something else that appears quite frequently in recommendation systems, and it's super, super, super important, is that if your matrix is block diagonal, which means that if you rearrange the rows and the columns, you get non-zeros here and non-zeros there, and you run SVD, you might get the wrong results. So in a way, you should always run a test on your matrix if it is disconnected. Basically, if it's block diagonal, it means that it's these two completely disconnected components. For those of you that have seen past meetups, whatever sessions with me, especially the ones who came in the first data session, mentioned that any matrix, if it helps me a lot, it might help you to think about it as a bipartite graph. And here you have the nodes that correspond to users, and here you have the nodes that correspond to volumes. And you have basically connections. And the idea of collaborative filtering is that I don't really have any relationship between users, but by following paths through movies, I can always connect users. Okay? That's the main idea. Now, what happens is that if this graph is disconnected, basically it means that some users will never be connected because they don't have common movies. Okay, two separate groups are not going to be connected. And this is going to full SVD. You remember in the previous example over here, I mentioned that you will get non-zero values here and non-zero values there. The truth, though, is that SVD might get tricked depending on the implementation and put garbage over here. Garbage here, garbage there. Okay? So that's very important. Now, let's move to the last part, and at 1 o'clock we will start coding with. Actually, I've coded most of the stuff for you in Python, but you can look at them, and we're going to make some comments, and you can do your own things and extensions. Okay, so we started with our initial data. Now, in a way, we factor them. And here's like the question, what is the purpose of recommendation engines? To make recommendations, okay? So at some point in your website, your web application, you have this user here, and you want to ask, recommend movies or products for him. So how we do it? Technically, what you have to do is you have to take this, run the dot product with this, and sort them and see which ones rank the best. Okay? Because don't forget that on a perfect world, if I was, let's say that this user over here, no, this is our user over here. He had made some recommendations. Okay? Now, if I go and I multiply his vector with the corresponding movie vectors, I should reconstruct this exactly. Okay? Is everybody with me? Do we have any questions? Is everybody from the remote students, if there's still any? So actually, all the non. So the question was, what if we had a question mark? So all the zero values are actually not zero. It doesn't mean that he has rated the product zero. This is exactly what you're saying. These are question marks. It means that we don't know. And this is what we're trying to predict. So basically, if you were going to the movies that he had rated before, and you do this dot product between this and this, you should reconstruct the exact rating or something very close. Now, if you do the dot product with the other movies that he hasn't rated, you should get the predicted rating, like what you think he would rate that. So basically, if you do that with all the products, and you see, let's say you have a rating system from 0 or 1 to 5, never use 0, it's not a good idea, then you will see that for some products it will say 4.8, 4.9. So you pick those and you recommend them to him. So that's like the next part. So far we did the training of the system, which is SVD, and now we're doing the serving, the recommendation. Now, of course, I always want to remind you that we are in shallow waters in the sense that Amazon or Netflix will never do that because the problem is diversity. Let's say that you just happen to have a bias towards horror movies, but you also like other movies, especially what happens in a family where Netflix is, one account with different modalities. You also want to take your movies over here, run a k-means clustering to form clusters, and make recommendations from every pool. Okay? Otherwise, it will be boring. Like especially for companies that they recommend clothes. Like you don't want to go on a company and then get only shirts. You also want to buy pants. But what happens if you just only rated one thing, or shirts? So the problem is that every time a user comes and you have 1 million products, you don't want to do a linear search over that, even offline. If you think about that, let's say you have 10 million users and 1 million products. If you want to do the comparison all with all, that could be more than 10 billion searches, 10 billion evaluations. So for that reason, we're using what I would call here, I think I mentioned that before, I'm mentioning again, it's a data structure called KD tree that basically takes this, I see some people recognize that. Have you seen KD tree before? Because you mentioned that, okay. So the KD tree is a hierarchical structure. That's actually one of the areas that I specialize. So basically, you take all these movies or users, whatever, it depends on whatever you want to find, and you place them on these lists, and then in log n time, you can find the top matches. Okay. So do we have any questions so far? Do we get the architecture? Like, do we get the feeling, the point behind that? Any questions from the online crowd over here? Angelo and whoever else. I can't tell who is remote because everybody's connected to that. Yeah.
So for each user, we have a vector, which is their rating.
Mm-hmm.
And then for each of the columns, we have another vector that corresponds to, I think, the head of the column.
So that's not, no. Are you talking about? So here's the thing. The users, like in the beginning, like this is the initial matrix. Let's call this matrix A. This matrix over here has their pure ratings. Okay. Now this matrix U over here, it has their summary. So this is not like the numbers you're going to see here are not ratings, but it's more like their profile, that this user is 10% into this type of movies, 30% on the others. Like that's what we're trying to reduce. Like another way to do it is somebody would say, okay, Nick, why should we bother and do that? I could just take, user 1 on the initial domain on the rating, and then user 2 over here, and run the dot product between them, and find how many common movies they have, and say if the users are similar. And if they're similar, I will just recommend the user, the movies from one to the other. Now, I'm not going to tell you why this is wrong. You have to think about that. We're going to see that later. But keep that in mind, that this could just say that Nick and Amber, they have or they don't have some common movies. It wouldn't really predict your ratings. It could just say that if they have many in common, the ones that they don't have in common, they're probably the ones that they're likely to see. But the problem is that, I like some movies with Amy. Amy likes with, say it again, Soy. And so basically, there is a link, an indirect link between me to Soy through Amber. You remember I plot the graph before, you can do all these paths. So you're not really exploiting all these paths to discover movies. So right now, I want you to start your Python interpreter. I use IPython. Does everybody have, I forgot about that, to tell you to install IPython. Do you have IPython? Can you install it? It's very easy. So it would be much easier if you could install IPython. Okay, now we'll have Ubuntu. So open your Python interpreter. Okay, I see. Who's KJ? KJ is remote. KJ is Seafried. Isn't that an actress or no? Oh, Seyfried. No, okay. So everybody has IPython open? Have you installed IPython? Okay. Or if you have any other Python environment, I think Windows, they do have an interactive Python environment. Okay. So import the CF package that I mentioned. Did you download the CF package that I... Okay. You don't have the SciPy? Can you install it? Can you install SciPy? Do you have SciPy installed? You're running Windows? So, sorry. What is the software? It's IPython for, where's Tiru over here? So, is it easy to install SciPy? How do you install? Because they're young students, they don't know.
Are they on there? I can put the link.
Yeah, just, huh? So, do you have IPython? Do you? Okay, have you installed SciPy? Install SciPy. Have you installed SciPy, Amber? Okay. Okay, sorry, but meanwhile I can have some of my. So, for those of you that they have Python and everything and SciPy installed, import CF. You can also open the file, the cf.py, and use load data to load, let's say, one of the recommendations, one of the files, like the u.base. I think I have it here in the beginning. Yeah, cf.py. If you go to the meetup group, under files, did you download? Do we have anybody from the remote students that have downloaded the cf.py file? Okay, somebody has done it. So, okay, you guys imported in IPython. So, run the function load data with the u.base file as an input. Okay. So let me run the commands. I'll write them. So, yeah. No, I'm going to write, I mean, depends on where you have installed the, it might be on a different path, I don't know. Or u1.base, yeah, that would be fine, u1. Okay. Now, once you load them, then you have to use this called factorize. I should have used factor, not factorize. That's not right. So this will run SVD, and we're gonna look inside the code and see it does some tricks to a simple normalization. And then we have to index this data. It's not working. You need a. So do you want another network cable? Might be a spare one. Are you sure? Okay. Okay. So no, I can see that's fine. Don't worry. Index data. Has anybody been able to run any of the commands that I'm typing over here? And so basically, just to anybody, have you been able to run anything, Noir? Mono? Any luck? You don't have internet? So what is the problem? We moved away from this horrible R, evil R. We went to Python. Hey, don't worry. Next time, what we're going to do is that we will run that on Mortar data. I've talked to you about this website. No, CF is not in SciPy. CF, if you go to the Meetup website under Files, I've also posted that on the Meetup, whatever, invitation. So CF is my module. I just wrote it this morning, yesterday. Okay. So we will run, I think the next thing is we will run everything web-based, assuming we have network, so that we don't have these sort of problems with Windows and Linux or whatever. So that's probably the best way. You can always use this virtual machine that we had from last semester. It's also posted on the Meetup wiki for those of you who run Windows and you have problems. So anybody so far been able to run this command? Yes, you're right. Factorize takes 2 arguments. Sorry, my mistake. So factorize, it takes the data and the rank of factorization. So remember, so let's put here 5. Okay, how do you do it here? Any luck? Sorry.
I'm still trying to change my working direction.
Okay. So did you change? So SVD requires, as I said, the factorization, and that's one of the things that you experiment. As you know, we don't really know a priori what is the number of latent factors. How many types of movies we have, or blah blah. So you have to play with that. Let's say 5 for the moment, and this is how you will cross-validate. So you will try for different numbers, and you see how your estimation or evaluation score, validation score changes. Global name eggval is not defined. Where are you getting this error? Is it in the factorize? Strange. Sorry, it should be, yes. So go inside the file, my fault, and go to factorize. Where is it? Okay, on the second line where it says eggval, replace that with egg underscore yes. So for those of you that get that error, replace. Yeah, the truth is that I ran that later. Egg val to egg val. Okay. So you haven't been able to connect. Do you want to go to the other table? There are some ports over there empty. Brian. So far, up to here is the sort of training, if you want, or creation of your recommendation model. Now you can say result or no recommendations equals CF dot find top recommendations. Okay. Yeah, we just mentioned that. Just go inside the cf.py file and replace this egg val with egg underscore val. It's a typo. Okay, for those of you that they use IPython, when you make this change, you have to reload the package. You type reload package, okay? Okay, so here's I think the file is you. So anybody who has been able to run all the way to index data? Samir, is there anything we can do? Are you having any trouble? So what is, you cannot install SciPy? So is it on your working directory? If you want to say import CF wherever you started Python, I don't know how it is in Windows. Like you have to say what is your working directory so I can find it. There must be a parameter. Sorry, how do you set that? Did you find that out? Yes. Are you using IPython or?
IPython's downloading.
Oh, okay. Mhm. Mhm. Sorry, that's a model. Sorry, it's my. So the output of factorization should be the model. Yeah, I see what you're asking. Let me rewrite that. Mod. So you see, I changed that. That's where the model is coming from. Can you Google to see if, like, so your problem is that you cannot import CF?
I have not been able to change my directory to look into. Do you type that in?
So do you have an interpreter that you have started somewhere? So do a CD to the directory where you have, or actually start this in the directory that you have CF. Close that. Yeah. Go to the directory where you have CF and start Python from there. So Angelo, So I'm just explaining. So the factorize does the SVD factorization. The index data takes the data and puts them on a KD tree. And then the recommendation, what it does, it says, okay. Yes. So, what happened? I just changed it. Can you see the whiteboard? It says model equals factorize my data, comma 5. Really? Okay. Yeah, we pay so much money, it doesn't work that great. Cisco. So you can specify the full path like load data. Yes, you're right. This is how you specify it, the full path. No, I think the problem Angular they don't know how to import. Like at some point in Python, you have to, when you in the configuration file, I can't remember how you do that in Windows. You have to say in which directory to look for packages. So they don't know how to do it in Windows. So my advice, if you're using Windows, start your Python in the directory where you downloaded CF, and then you will be able to import it. So I was just saying that, when you type index data, the index data will create a KD tree on both users and movies, okay? And then when you say CF finds top recommendations, you are passing this index into your function. Number 4 is the user number 4, and 10 is find me the 10 top 10 movies. And this will return you the index of the 10 best movies for this user. And then you can load actually the movie names, and you can see which movies they are. Like these are the next two commands. So are we doing better? Is it? It is. Must be there. CF. Are you sure it says? Oh, it's actually cf.load movies. Sorry. There is actually a web. Does anybody know there's a web version of IPython where you can share your editor? I think. Never. So let me. Yeah. So it says Amlet. Like if you go inside the CF file, you can see other functions where they say find similar movies or find similar users. You can use that too if you want to sort of evaluate. So you can go and say, for example, here, other or close movies. CF. Movie number 14. Then you can see, like, if you say movies 14, you would see the name of that movie if you recognize, or you can just open the file and see the one that you know, and then you can say movies and see which ones are the close ones. So some of you were able. So what about the students there, the PhDs? Were you able to run it? What can you? Sorry. So it doesn't find. You cannot find the file u.item. So let me see how I can. So what is? So what is the?
So I downloaded IPython. So how do I run?
Just open a command prompt. Go before what you had. Just open a command prompt. Like a command here, like this one. That's IPython. So are you already Python? Exit Python. Open it. Just a command prompt. Yes, the command prompt and you type IPython. And this is the no, it's the same. What's the problem? I downloaded from the same site. So why are you getting different movies, Angelo? Like, did you use the u.base or the u1.base or there's different files? I'm not sure if all of you use like you can use the u1.base or you can use the ub.base or there's another one called u2 base. There's another one called UData that has all the. So Angela used I use the same, and I think I got the same results. I don't have them with me right now, but let me see if I can help. So is it working now?
So I'm in here.
Did you type so go to the directory when you downloaded CF. Where is the CF.py? Sorry. You can re-download it somewhere that you know. How is it going? Did you start IPython on the directory where you had? Oh, sorry. Just close it again. Just type exit here. No, you don't have to close it.
The trouble is that I don't have SciPy and NumPy installed in the where I downloaded.
Okay, let's do something else. Open a command prompt where did you download the C? Okay, where is it?
It is here.
Okay, go to that folder. Like open a command prompt and go into that folder. No, I think there's a way. I don't really know Windows that much, but I think if you could. And go to, where do you go to? Do a paste there, CD, and then do a paste. No. Paste with your mouse. Okay.
Oh, okay.
Now do Python. No, import CF. What does it say?
I can't find SciPy because I installed SciPy in Python. That's SciPy. Oh, that's SciPy.
Yeah. So how do you install Python? Where have you installed Python?
I installed SciPy in my Python directory in the libraries.
Can you give us some help? Who? Yeah, put it there. Are you running Windows there? Hmm? Okay, one of you will come and help them run it here. How do you do it? And you just clicked and installed? Mm-hmm.
Alright, let's try it. Okay, now it's in there, so I'm going to say import.
You do import SciPy here. Okay, it worked. Now go to the.
Now
okay.
we do this.
Okay, so. Okay, do we have any questions from the remote students? Is everything resolved? Like, do we have any other success story? Anybody else who managed to to run it and see, play a little bit with results and the movies? No. Indeed, I saw that KG posted, and it was it made sense. Hamlet and Secret Garden. These are similar movies. It seems to me the system is working. Let me go around and see how people are doing. Samir, So what you can run? So have you installed SciPy?
Yes,
I installed NumPy too. Hmm? Say that. So why don't you install the 2.7 Python? How are we doing here? Brian, did we have any success? No. The SciPy? Or the...
I already had SciPy.
You don't have to install it. You just open your IPython or Python interpreter and you just type import CF. That's all. You don't have to install it. Yeah, okay. What? Sorry.
They have the this is the recommendation user 0, right?
No. Let me explain the results. So you say now, find the recommendation for user number 4, the 10 best recommendations for user number 4. So this is going to return you 10 recommendations. So that's like the top recommendation when you see it like movie. Yeah. And then
okay, for user number 4. And we find similar movies. What is the index?
The index, so I'm explaining again, the index is that, as I said, you do SVD and you get these vectors. And you have to put these vectors on a KD tree so that it's easy to search. That's what that is. It has the movies. It's a thing about as a hash function. It's a tree. It's like a binary tree when you do sorting in binary tree.
Okay.
So that's what it is. But, okay, so you're printing and you are watching there. So if you put here 1, 2, 3, you will see the other movies that take movie number 34. You can check which is or is it 34 or 14? To see which one is movie 34. If you do movie 34, you can get the title, and it finds 5 other similar movies with this one. Okay. Well, welcome. So how is it going here? You guys working? So did you find movies that they're similar? Did it make sense?
Oh, yeah.
Okay. Are you ready to... Are you the co-founder?
No.
He's like...
I was showing him my classification agent. It's out to replace his code.
I see. So you see how it works. Like, is it simple? You can... No. It's working. You'll get there. Welcome. Let me give you an idea. The same method is used for classification and Obama and president. These are like words that have the same meaning. So, in some documents you see them co-occurring and some or not. So basically this does sort of kind of like a compression and it would like to President Obama and President Obama. I think that two cultures, they seem to be the same, because we can give you more relevant results. So I think please more sticks. So I think it's the singular value decomposition is more like a computational method. Like when you think about graphs, is that like you go from user to a movie, user, you do this bouncing, and that's exactly the mixing. Now, if you let's say that mathematically, it does thing on SVD. It's more like a diffusion on a graph, or this bipartite graph. It means that, I know you and you know him. If I strictly connections, I would never know about him. But on a second hope, I can find it. I can start using. Now, some comments, because we are going towards the end, that I want to make about this method. Over there. It's Brian. It's scared to see Brian. We'll put him as our sponsors. What's your company that for the cinnamon sticks? They are very high quality, just like our algorithms in our class from Alon's. So is it working? No? Like, do you have the VM that I have from the previous class? You should download the virtual machine. So what is the problem? Did they try to help? Did they help you? Why aren't they helping you? Why are you helping the ladies, greedy boys? Like, did you help them do the windows? But it's not. Oh, audio. Yeah, sorry, I was a little bit away. Is the audio? Yeah, it's better now. So it's the distance. It's this whatever Bluetooth. I don't know, whatever headphones. So I was just saying that this particular algorithm, the way that it's implemented, would probably scale very well. Like if you could use that. Like I would recommend you to go to the Netflix website and download the Netflix data set and try the same thing. It will still work.
Python 3.3 has the has key for a dictionary. It's saying that a dictionary object has no attribute has key.
Oh, so you have a Python 3.3?
Yeah, is that the problem?
Might be the problem.
Oh, yay. Okay.
I should have actually, I've never used Python 3.3, but somebody asked me if it makes a difference. So do you think there is a big difference? Do you know if there's a big difference?
Not brave enough to go past 2.7.
Yeah. So can you install? Why don't you install the Python 2.7? It says, yes. So Angela says 2.6 2.7. So you're getting some errors?
Yes.
So that 2.7 will be easy to install.
Okay, I'll put 2.7.
So I install the previous one before you do it. Okay. Oh. I think I have something on the. I have some books on the Meetup that I recommend for machine learning. Now, for recommendations, there are papers. There are some books. There's one book from Cambridge University Press that is pretty good. That's called Introduction to Recommendation Systems, something like that. And there was a previous Meetup where there's some work done by GraphLab guys, which again points to some papers. But so, what's your background? Who are you working with? So what's like your topic? So you're the bioinformatics.
Yeah. It's a little,
So you know about these things. Mm-hmm. So if you really want to encompass machine learning, I'm saying there's this book from Kevin Murphy. It's called Machine Learning something. I have it on the website, which is probably the best book to have. It's pretty complete and very, it has almost everything in there and very well written. It has everything, not just recommendations. But recommendations, recommendations kind of like an umbrella. They, as I explained, it's sort of clustering. You can use them for classification. You can also use them for prediction. It's kind of like a little bit of everything. So, are you like, what year are you in your PhD? Okay. So you're pretty senior to read. I can point you to some papers then. Okay? They're doing are you doing recommendation system? He's doing recommendation systems. They're from signal processing. Yeah, ask me.
For extending this framework to the Hadoop, you mentioned there's a website.
Motor data. So basically, first of all, that's a good question. The way that this is implemented is this is a sequential algorithm. It's like you didn't see that on the MapReduce function, whatever. Now, what you can do, the easiest you can do is kind of like run Bootstrap, which is take the data, sample them, build 100,000 recommenders, like that's like your map function, and then the reduce will be the combination of those. So let me put it that way. So for make sure that each mapper has all the users, and maybe some of it doesn't matter, but it should have all the users. So basically think about that. You take a subsample and you generate recommendations for every user. Each subsample will probably generate different recommendations. If you do a voting scheme and you say, okay, walking on the clouds or walking the clouds, whatever they said, or Terminator was recommended 10 times out of the 100 times that we ran that, then it's probably a good recommendation. Like a more non-parametric or Bootstrap way of doing that. No. No, it will overfit at some point.
Okay, so what? Yeah, you're right. So how can you find the optimal,
with cross-validation, basically. There's another thing. SVD is kind of nice because it's also, I wouldn't say convex, but it always converges to the same result. Now, if you use like another problem is that, so it means that every time you add a K, the reconstruction improves, but that doesn't necessarily mean the generalization improves. But if you use other methods that they are non-convex, adding an extra one might actually reduce even the reconstruction error because these are non-convex methods. So how is it going? Are you downloading? Okay, 2.7? 2.7, don't
do 3.
So, but it's better than R, you have to admit. So I don't want people to get disappointed. Like in the previous course where we had R, it took much more time to get things running. Is it running for you? So are you downloading 2.7? Like my advice, and that's what we did and I should have mentioned that, but again, I've been super busy lately. I didn't have time to prepare things as I wanted, and bear with me on that. I'm just doing that, out of courtesy. So I can't make it like a full course. So don't get disappointed. My advice would be use the virtual machine. I have uploaded a virtual machine on Ubuntu one, which is much easier to run this thing. So super easy.
I love that.
So if you go to the meetup, you will find it over there. Where's the virtual machine? Don't do it here because it's like 4 gigabytes. It will take time to. The one that you downloaded? Maybe it's more. Is it 30? Maybe it's 30. I don't know. Okay. 4 was a different one that downloaded. Yeah, I take it back. What wrappers? The Mortar data? We don't need any wrappers. You just go to this website, Mortar data. You put your Python script. So you have to, there is a way. First of all, you have to upload your data onto S3, Amazon S3. They have the instructions. And then you have to take your data and split it into, actually this is already split in key value. So you have to modify your Python script how you read your data. Like its Python script will read a stream of like, you know how MapReduce doesn't read a file. MapReduce gets line by line as a stream. So you have to write your function as the mapper, where you assume that everything that comes. So basically, you start getting lines out of a stream, and then you stop. You build your the SciPy matrix, and you run it. I need more time to explain to you, but if you read how MapReduce works, it's fairly easy, basically. So say that again, sorry. So basically, so here's the thing. What is important is that when you run this independent, like these subsamples, is that there's some overlap between them. Like if you run a recommendation for the first 100 users and then for the second 100, then you won't be able to combine those. So you have to make sure somehow that it is, there's an overlap between users and movies. And okay, movies it's easy because movies are typically small, so you always have the same range of movies. But you have to make sure that there is some overlap between them, the users. So welcome. And there are some smarter ways. That's kind of like a naive way. That's not the best way to do it. But would be. But even with our implementation, if you launch an 8XL Amazon image which has 64 gigabytes of memory, you can do pretty big problems. So that's like something. That's one version of collaborative filtering. There's more. Okay. I think the term collaborative filtering is used for a different factorization method, not for SVD. I think SVD they call it LSA or LS latent semantic analysis. The collaborative filtering is like a broader term. To be honest, I was never good with the names. It's either this or it's more like a low rank factorization rather than. So, if you finished, you're free to go. Or you can stay up. Probably have some time until 2 where I have to catch up with some other work. How is it doing? Is it no? Mm-hmm. Mm-hmm. Well, that's also a general term. All of them are low-rank decompositions. So, any questions from the remote students? We're basically done for today. I hope it was useful. Mm-hmm. Mm-hmm.
So to change, so right now it's open what directory you're in, right? So
Yes.
So you want to can we use whatever directory
when you're saying dimensions, now we have user item rating, and then you have a user item rating timestamp. Actually, this data set has also timestamps too. So the first algorithm for that was called SVD++, or the libfm, the factorization machine. They also do that. They can handle more dimensions. Now, you think that SVD is in 2 dimensions. You can also add all these dimensions and make a tensor, and you can do what they call tensor SVD. If you want to put user, item, time, gender, location, rating. Okay, so you can have different dimensions and the rating, and that's a tensor now. That's called a tensor. Yeah, this is like a 2-dimensional array. So you start the first dimensional array is the vector, the 2-dimensional array is the matrix, the 3-dimensional array is like a tensor, this cube, and then you can have more. Okay, I think I'm gonna. Actually, I'm not gonna turn off because people are probably looking at. In relativity, tensor is used in physics, relativity a lot. You have like the time tensor. In theory of relativity, you have space, time, and velocity. Like you have the 3 dimensions plus time, so you have 4 dimensions, the 4-dimensional tensor. So tensor is like a cube, like an array is just a square. The tensor is a cube, where you have elements in 3 dimensions. You have I, J, K, 3 coordinates. So that's a tensor. So are you talking about Prezi? No, talking about presentations. Which one?
I use GD5.
Oh, Okay, so I guess nobody's using. Are you using? Did you take notes, or actually I should post that somewhere? So were you able to install Python?
I was, but I couldn't get it to import into
Okay, guys, we are signing off here. It was good to see you. We'll see when we're going to have the next session. Maybe more time. Bye-bye.